Welcome everyone to today's video. In today's video we're going to take some parametric data where we have two samples and we're going to undertake hypothesis testing. And the two samples are independent and we'll be using Excel. So we're going to conduct a two-sample t-test for independent samples using Excel. So if we go to the Excel solution, as you can see on the screen, so what we've got here is we've got two groups of data, Group 1 and Group 2. And what we do is we create a step structure for our hypothesis test. So what we'll do first is we'll go through this step structure that you can see on the screen. Then we'll do the data analysis solution. And a later movie will look at this from SPSS perspective. So the step one hypothesis is that the two samples are drawn from normal populations, normal distribution populations, and the population means are equal. So you've got sample 1 as a population. So population 1 mean is the same as population 2 mean. And the alternative is that they are not equal. If I just make that a little bit bigger for you so you can see. Just make it a little bit bigger. That's better. Okay, so what we're going to do is we're going to compare two sample means where both population distributions are normally distributed. The population standard deviations are unknown but are assumed equal. Now please note that we will also look at this from the perspective where the population standard deviations are different. But first we'll look at it from the point of view where the population standard deviations are known. You'll see on the right hand side there's the equations that we use. So we got for equal variances, we got the t-test equation. There's your pooled standard deviation, and there's the degrees of freedom. Okay, so what we need to do first is we need to state what our significance level is, and as you know we take 5%. Then we need to know what N1 is, or NA, which is the size of sample 1. So we count B4 to B46. And that gives us 43 numbers. We calculate the sample 1 average using the average function, B4 to B46. And also the sample standard deviation for sample 1, which is B4 to B46, using stdev.s. And we repeat it for sample 2, and then we can calculate the mean difference between the two sample means, which gives you xa minus xb, x bar a minus x bar b. Remember, where the null hypothesis is true, mu a minus mu b is just 0. Okay, and then once we've done that, we can then calculate this pooled standard deviation, which comes out to be 2279.8498 to 4 decimal places, and then we can then calculate by substituting that number into this equation. We can calculate t, which comes out to be minus 1.2992 to 4 decimal places. Now that's not a particularly big number, so we're probably fairly safe to assume that the decision will be to accept the null hypothesis as true. So based upon the sample data values being representatives of the populations, number 1 and number 2, etc., the evidence would suggest that the null hypothesis is true, so the population means mu1 is equal to mu2. But we need to confirm that statistically, of course. So what we need to do is we need to know what the degrees of freedom are from this equation here. So we get 76 degrees of freedom. We need to calculate a two-tailed p-value because we've got a two-tailed test. And we use the t.dis.2t Excel function, and the two-tailed p-value is 0.1978. Well, that confirms because that's a lot bigger than 0.05. So we know that we're going to accept the null hypothesis. So the evidence suggests that the two population means mu1 and mu2 are equal. Now, obviously, the alternative is to just calculate the critical values, the upper critical values and the lower critical values, and you can do that using the Excel function t.inv.2t, and you can see there that the upper critical t-value is 1.99. The lower is minus 1.99. You'll see our value of t lies between that number and that number, which is in the region of acceptance for the null hypothesis H0. So those two decisions should be exactly the same. So the p-value should give you a decision that the null hypothesis is correct, and the critical value compared to the calculated t-value will give you the same outcome. Okay, the alternative, of course, is to undertake confidence intervals, and you'll see in the book that we've included how to calculate the confidence intervals for mu a minus mu b. So you rearrange this equation to get mu a minus mu b equal, and then you calculate all the particular values as you can see there. Okay, the second bit is when we assume that we have unequal variances, and remember the equations are slightly different from the book. So look in the book, they're the equations that we would use, etc. And again, if you scroll down, you can get the pooled variance. You can calculate t. Sorry, scroll down, sorry. You can calculate t as minus 1.24 this time. And now this time, you have to calculate degrees of freedom. And I've split that up into a numerator degree of freedom and a denominator degree of freedom. So you can see what I mean there. There's the numerator and there's the denominator. So the degrees of freedom comes out to be 56.17 to 2 decimal places. We can now calculate a two-tailed p-value, which is 0.218, and that, remember, is bigger than 0.05, so we still accept the null hypothesis, and we calculate the corresponding critical values as well, which are minus 2 to plus 2. So you can see that our calculated value there lies between those two values. So again, you would accept the null hypothesis. And the corresponding confidence intervals are listed there. Now the reason we did that is because when we look at SPSS, SPSS will automatically give you all these numbers. So it'll give you the t-value for when it's pooled, it'll give you the t-value assuming unequal variances, it'll give you the corresponding p-values, and it also give you the confidence intervals as well. So that's the Excel solution, but what a surprise, we have a simpler method in Excel. So there's my data, just like before. But this time we can actually use data analysis. And if you scroll down, you'll see you've got a t-test for equal variances and a t-test for unequal variances. So if I click on that equal variances one, then we end up with this menu, which is this menu here. We fill the details in, we click OK, and we get these solutions here. Okay, and if you compare those solutions with the long method that we've devised there using the Excel functions, you get exactly the same answers. And correspondingly, you've also got unequal variances method there. Okay, so again, if you wanted that, you just click on data analysis, the unequal variances, click OK, and there's your menu. Okay, and when you put all the values in, so if I just scroll down, there we are, I filled them in there. So when you put all the values in and then click OK, you'll get these numbers. And then you compare these numbers with these numbers here. So these numbers here and there, of course. Okay, so that's the end today. It's a little more cumbersome because you've got two basic t-tests that are applied dependent upon whether or not you pool the standard deviations because you assume they're equal or you have them unequal, etc. Okay, bye for